Each of the 5 sides and the 5 diagonals of a regular pentagon are randomly and independently colored red or blue with equal probability. What is the probability that there will be a triangle whose vertices are among the vertices of the pentagon such that all of its sides have the same color? So there are going to be a lot less instances where these such triangles are all different colored, meaning they're not all the same. Every triangle is not the same color. Every triangle is not monochromatic. So we're going to break this into cases and look at how many of these pentagons exist, which will then help inform us of how many triangles there exist where all the sides have the same color. So for case 1, we're going to have a regular pentagon, and it'll be such that all of the sides and diagonals emanating from the topmost vertex are one color. So they're all blue. And then from there, we can fill in. We know this has to be red, and just fill in as much as we can. And we've already reached a contradiction. That side, when we color blue to make sure this triangle isn't all red, that triangle is all red. So in this instance, when the 4 of the or all of the sides and diagonals emanating from the topmost vertex are the same color, we can't get a regular pentagon where all the triangles are different colored. So case 2. So this is going to be a situation where we have 3 of the sides and diagonals the same color. So we'll do all blue here, and that'll be red. So that has to be red. That would have to be red. And right here, this has to be red to make this triangle not all blue. But when you do that, this triangle is all red. So that doesn't work. And another case we can look at here is we chose 3 of the sides and diagonals such that they're all adjacent. Just to make sure, we'll check the case where they're not all adjacent. So in this case, like that. That would need to be red. That needs to be red. And additionally, that would need to be red to make this triangle not all blue, but we end up with this triangle all red. So that won't work. The last case to look at, case 3, is looking at a regular pentagon, again, such that 2 of the sides and diagonals coming from the topmost vertex are the same color. So go like this. Great. And then from here, we see that this has to be red. This has to be blue. But then this could be blue, and then from there we have that here, red, red, and then this bottom would be blue. So this works. And even with the same formation, so looking at the same pentagon, again, this has to be red. This has to be blue. This middle diagonal could also be red, and it works out. That also works. And you'll find that similar to what we did up above, for regular pentagons, for example, with still the two of the same color coming from the topmost vertex, but the configuration can change. So we can have something like this, where the two same colored sides and diagonals are not adjacent, and you'll find that it still will work. Just to finish this out, we can still make it such that it works here. That works, and we can color that middle diagonal so we get another that works. And you'll find that you check the other configuration such that from the topmost diagonal, if you look at this configuration, and like that, you'll find that that configuration will also lead to one that works. And there will be another, the same way that there's a subcase here, there will be a subcase for this one. So basically, it'll work every time that we have two colors emanating from the topmost vertex. So since there are 4 choose 2 ways to color from the topmost vertex, there's 6 ways to color from the topmost vertex. And then once you do that, you get one, a pentagon that works. Then there's always going to be a subcase where, in this instance, we could color this diagonal across red, whereas that one was blue. So every time there's going to be a subcase, so we multiply 6 by 2, since there are 2 ways to color the pentagon from the same configuration of blue or red emanating from the topmost vertex. So that means that there are 12 ways to color a regular pentagon such that none of the triangles are monochromatic, the same color. That then leads us to look at the bigger picture. So since there are 5 plus 5, 10 sides and diagonals total in a regular pentagon, and we can color them either red or blue. That means that there are 2 to the 10th, which is 1024, configurations of how we can color this regular pentagon. And since there are 12 ways to color it such that none of the triangles are the same color, that means that there are 1024 minus 12, which is 1012 ways to color the regular pentagon such that we have at least one triangle that's the same color. And so what we're trying to find is the probability of, when you color this regular pentagon, one triangle being, at least one triangle being the same color. So that probability is going to be there are 1012 ways to do that, and 1024 possible ways to color the regular pentagon. And reducing that fraction, we get 253 over 256 for the probability we are looking for. So the answer is choice D.